Hello everybody, my name is Haiyuan Wang. You can call me Harry. I'm the instructor for ISDA609, Mathematical Modeling Techniques for Data Analytics at MS in Data Analytics program at CUNY, City University of New York. First of all, welcome to Data Science. Welcome to Data Analytics. And also welcome to the MS program in Data Analytics at CUNY. So in this video, introductory video, I would like to introduce you to the realm of math modeling techniques. What is math modeling? Why is it important to have math models? And also, I will provide you some real-world applications and real-world examples of how we may use math modeling techniques to solve those problems. Hopefully, by the end of the semester, you are able to apply all these modeling techniques. So I hope you have a wonderful semester and you have a productive semester and you can learn a lot from this course. So without further ado, let's get started with the slides. Okay, so let's get started. So what is this all about? First of all, I would like to briefly explain my background and also my contact information so that you can contact me when needed. I will discuss what is math programming and math modeling, and why do we need math modeling, and what type of real-world problem that can be solved by math modeling techniques. Let's get ready for the course. So here I have my email, my phone number, and my office location. I actually don't have a physical office on campus, but we can always meet on campus locations by appointments. So you can either ask questions through the black box system, or you can send me an email or call me. If you don't hear back from me in 48 hours, please send again. I could have missed the message. But in general, I'll try to get back to you within 24 to 40 hours time frame. So what is math modeling? From Wikipedia, this is a definition for mathematical model and mathematical modeling. So in general, it is to use mathematical concepts and language to describe the real-world problems. So a model can help you to explain a system, to study the effects of different components, and you can also use a model to make predictions based on actual observed behavior. So math modeling is actually used in many disciplines, including physics, biology, earth science, and some other important subjects such as computer science, artificial intelligence, etc. So it can take many forms. Can be dynamic systems, statistical analysis, can be differential equations modeling, can be game theory models, or can be mathematical programming, including linear programming, nonlinear programming, and integer programming. All these topics will be covered in this course. So stay tuned so that you get all this exposure to all these concepts. So based on the model classification in Wikipedia, it can be linear versus nonlinear, static versus dynamic, so on and so forth. These will be covered in the course as well. So why do we need a math modeling? From real-world data, with simplification, we can build a model. And we can analyze the model and get some mathematical conclusions. We can interpret the mathematical conclusions so we can use those models to do predictions and explanations, which in turn would try to verify the real world data. So this is really a snapshot of math modeling. Why do we need math modeling? And also the intuition for this particular course. Meaning that we want to use math model to explain real world problem and to understand the real world problem. So let's take a quick look. Here actually I try to give you a brief overview of what types of real world problems can be solved by math modeling. Traveling sales problem, traveling salesman problem, also called TSP. It is one of the most classic example in network analysis and math modeling problems. So let's say if a UPS driver wants to visit location A and B in a particular hour, and then he has to make a decision on go to A first or go to B first. If we use this number to represent the cost that it takes from here to from UPS to A, and also this cost from A to B, and also 5 from UPS to B. And note that this direction is bidirectional, meaning can be from A to B, can also from B to A, and the cost is the same. But from A to UPS, the cost is much higher than from UPS to A. So as you can imagine, if you visit A first and then B and then UPS, the cost would be 3 plus 4 plus 5. So the total cost is 12. But if you, on the other hand, if you visit B first, a driver goes to B first and then go to A and then comes back to UPS location, and the total cost is 5 plus 4 plus 10, which is 19, which is much larger than visiting A. So the optimal route would be from UPS to A to B and then come back to UPS. So this is really a simple example of TSP. What if we have more nodes? We have 20, 50, 100 nodes. It can be really complicated. So I'm going to go through this example along with some other examples as well, so that we can get a sense on what kind of real-world problem can be solved by math modeling. So I'm going to go over travel salesman problem again in a larger scale, and some linear program, shortest path problem, Google PageRank algorithm, and social network analysis. So let's go there and take a quick look. First problem here, travel salesman problem. So here, let me go down here, and then so for example, if the UPS driver needs to visit all these 7 cities, which one would be the best route? Then if you look at this current optimal solution is 262 changed to 249 just now. And as you can imagine, it probably takes multiple iterations to get to this number. And turns out this 249 is the best solution for this particular problem. But with more nodes in the network, it could be more and more difficult. Okay, the second example that we see here is a graphical representation of a 2D problem. So if we look at this particular equation, maximize 15x1 plus 10x2 with some constraints. Constraints is x1 is less than or equal to 2, x2 is less than or equal to 3, and the sum of them cannot exceed 4. And both of them has to be positive. So let's say graphically how it looked like if we want to solve this problem. Let's start some constraints. X1 has to be in this range, and X2 has to be belong here. And the third constraint is here. More constraints, non-negativity constraints. So this would be the feasible region, but we can discuss more in detail later in the course. This is just to give you an overview. This is objective function z equal to 0, 15, 30, 45, 60. There you go. This is the optimal solution, actually, meaning that if we keep moving this objective function, we can find the optimal solution here. Actually, I just didn't. This is the last point. This is the optimal solution, z equal to 50, because this is a feasible region instead of here. But we would explain more detail in class on this particular problem later on. And Dijkstra's algorithm for shortest path. Suppose we want to travel from O to T. What's the best route? What's the least cost route to go from O to T? So this algorithm, let me fast forward very quickly. So essentially saying that if we want to travel to A, we need to make a decision whether we want to travel A, B, C first. So as you can see that OA would be 2, OB would be 5, OC would be 4. So it probably make more sense to go to OA. Keep going and to see which one would be the best for next step. If we keep going, fast forward, and then this is a solution. It says that it's better for you to go from O to A, and then A to B, B to E, and E to D, and then D to T. And then the total cost is only 13. On the other hand, suppose you want to go from here, OCET would be 4 plus 4 plus 7 is 15. So this is the shortest path problem. So let's take a look at next problem, which is PageRank. So Larry Page at Google actually invented this algorithm. That's why it's called PageRank algorithm. Essentially, the algorithm is trying to do one thing, that is to rank those web pages to see which one is more important. That's why when we do the Google search, we get the most relevant results. So based on this particular example, E looks like could be one of the important nodes, but because it is connected to so many nodes. But it turns out it's not the case. C is much more important than E just because C is connecting to B, communicating to B bidirectionally, and B is one of the most important nodes in this network. Let's take a look at some a very hot topic on social network analysis. So assume that, for example, in all these nodes, if we have so many different nodes in a network, assuming each node is representing a person, then we can see all kind of communication in the system, and later on we can identify that some of the cohesive groups are talking to each other, and these people are talking to each other. On the other hand, these people are talking to each other, and these nodes don't really communicate with the rest of the network that often. So this is another example that we saw here. Okay, so let's go back to the slides. All these are very classic examples. If you follow the course, and then at the end of the course, we would be able to understand better on all these examples. Of course, these are only some of those examples. We would learn much more than this. So as you can see, it's very intensive in terms of mathematics. So I hope you would follow my notes and the textbook very closely and ask questions if you have as early as possible. Don't be afraid of any questions. I would work with you together and let's learn together. And I hope you would enjoy the course. Have a productive semester.